Mr. Hassan's Maths channel, and I'm now going to be answering question number 9 from the May-June 2024 Pure Mathematics P1 paper. This is paper 1, variant 1. This is from the AS level 9709 syllabus, and we are asked here in this question, we're given this diagram which shows part of the curve with the equation y equals 1 over 5x minus 4 to the power of a third, and the lines x equals 2.4 and the line y equals 1, and the curve intersects the line equals y, the line y equals 1 at the point 1, 1. As we see here, we've got to find the exact volume of the solid generated when the shaded region is rotated through 360 degrees about the x-axis. Okay, so I've got the diagram down here so that we don't have to keep on scrolling up and down. All right, so we have here this shaded region, which has to be basically rotated around the x-axis. So this has got something to do with what is called volumes of revolution. Okay, and the equation of this curve is given as this, right? Now, when you want to rotate an area around the x-axis, then what we basically have to do is as follows. We have to think of, and I'm just going to go through the reason for the formula. So I'm going to explain something. Maybe you don't really need to know this in detail, but just to make sure you understand. So it's like we take a small strip, okay, of this curve, so small, so thin. I haven't drawn it so thin, but so thin that it can be considered as a rectangle. Very, very thin strip. Okay, and this strip, its height is the y value of that point. So its height is y. And its width is a small, tiny amount along the x-axis, which we call dx. So this strip, if we were to rotate this strip around the x-axis, so if you're looking from this direction, for example, looking at this direction, what you'll see as this rotates around the x-axis, you'll see basically a cylinder forming. This rotates around the x-axis. Okay, you'll see some sort of a cylinder, a thin little cylinder forming, okay, which has a thickness of dx, okay, and it has a radius of y. Okay, so we know the volumes of a cylinder. The volume of a cylinder is given by pi times r squared times h. So in this case, the r is y, and the h is the small little bit of x. The h in a cylinder, like if you think about a cylinder, like this. This is like the thickness of the cylinder, which is our h, and this is like the radius of the cylinder, which is like y. So we can say that the volume of this small little cylinder is pi times y squared times dx. Okay, that's the volume of that small little cylinder. Now, if we find the sum of all the cylinders from the beginning, let's call that A for now, to the end, let's call that B, all right, then that will give us, and we find the sum of all those cylinders. Well, that's what happens when we integrate. When you integrate, it's just finding the sum of all of these little cylinders between A and B, pi times y squared dx, right? So this is the formula for the volume of revolution of a function. Okay, y equals something when you rotate it around the x-axis. Okay, pi y squared dx. If it's rotated around the x-axis, this is around the x-axis. If you rotate around the y-axis, it will be pi times x squared dy. Because in that case, your x would be your radius and your dy would be your height. Okay, so pi y squared dx for something revolving around the x-axis, and pi x squared dy for something revolving around the y-axis. Now, the issue in this question is, it's not this area that's being rotated around the x-axis, it's the area between this line and this curve. Okay, so there's something else that we have to now consider. Now, I'm going to show you in the next, in another part, towards the end of the video, I'm going to show you a method involving using this and also using the volume of the cylinder formed, the big cylinder formed when you rotate this line around the x-axis. But I'm going to show you also right now a different method, because sometimes you might have equations where it's not just a straight line and a curve. It might be two curves, the area between two curves, in which case you will be forced to use the method that I'm going to show you now. Okay, so you have two different functions here, and you want to find the area or the volume of the volume that's formed when you rotate the area between those two around the x-axis. So in this case, it's like we have another cylinder here formed by the one on the top. Okay, so when you rotate it, the area formed is going to be like the volume formed, so it's going to be like the shape of like a tire. Okay, if you look at it from this, you'll see basically you'll have an empty part there, and this part is where you're going to see all the volume, and it's going to have a certain thickness, right? So basically, we can think of the radius of the big circle. So with this, let's call this y1 and call this y2, right? So y1 and y2. So if you want to find the volume formed of this shape here, like a cylinder with a hole in it, then what we've got to do is we've got to find the volume of the big cylinder, take away the volume of the small cylinder. Okay, so in that case, you're going to have the volume is equal to, between A and B, you're going to have basically pi times y squared minus y1 squared minus pi times y2 squared dx. Okay, because you have to find the volume. Let me put it like this first. Pi times y squared dx minus pi times y1 squared dx minus pi times y2 squared dx. Okay, that's what we've got to find. Right? That's the volume of the big cylinder minus the volume of the small cylinder, which is going to be like an empty part. And that will give us the volume between them as you rotate the area around the x-axis. And we're going to find the volume between the limits of where you start to the end. It will find the volume of all of those cylinders, kind of like hollow cylinders between A and B. Right? So this formula becomes nice and easy when you kind of like simplify a bit. So we can see pi is common, so you can take the pi out. So I like to take the pi outside the integral sign. And then I'm going to have y1 squared minus y2 squared dx. So y1 squared represents the equation of one of the lines. In this case, that line is y equals 1. And y2 squared represents the equation of the other line. The one that's lower is the one that you put here. The one that's higher you put there. Right? That will give me the volume now of this shaded region as it rotates around the x-axis, leaving a hollow part in the middle. Okay? So this works whether you have straight lines or curves, whatever you have, this works. So that's why I'm going to use this method first, and then I'm going to show you the method because it's a straight line. You can think of this as like a cylinder minus the area underneath or the volume below it, okay, which I'm going to show you in a few minutes. So I'm just giving you the background behind where this formula comes from, where this formula comes from, right? So it's the volume of the big cylinder minus the volume of the small cylinder. If we consider a small thin strip of this, okay, so we want to find the volume of that region there, okay, and then you have to integrate between A and B. It's like you're finding the sum of all the cylinders formed between those two until you end up at B. Okay, so now I'm going to actually answer the question. That was a bit of background to know where the formula that we are going to use actually is derived from. Okay, so as I mentioned, the formula that we're going to use, we're going to call this y1, we're going to call this y2, and the formula that we're going to use is the volume is pi times the integral of y1 squared minus y2 squared dx. Right? Now y1 is equal to 1, y equals 1, and y2, the second formula, the one underneath it, is this one, which is, I'm going to write it as 5x minus 4 to the power of negative a third. Just using the laws of indices to write this on top. As we know, 1 over a to the power of n is the same as a to the power of negative n. Okay, so that's y2 squared. So we got to find and these are the limits a and b. So our limits are going to be between 1 and 2.4. So for our particular situation, we got the pi. Don't forget the pi. Always remember the pi. A lot of people forget about the pi and then it disappears somewhere in the question, and the answer will be wrong then without the pi. So you have between 1 and 2.4. Those are the limits of y1. Now y1 is just 1 minus, and then you're going to square this. Now when you square 5x minus 4 to the power of minus third, when you square this, 5x minus 4 to the power of minus a third, if you square it, you just basically multiply the power by 2. Okay, as we know, a to the power of n to the power of m, you just basically multiply the powers. Okay, so that's minus 2/3 it becomes. So 1 minus, and you're going to have 5x minus 4 to the power of negative 2/3, and you've got to integrate that with respect to x. So when we find the value of this definite integral, we will have the volume formed of the shaded area rotated 360 degrees about the x-axis. Okay, so now we have to integrate this, what's in here. So we have v equals pi. Now when you start integrating, the integral sign becomes a square bracket when you have this definite integrals. So you integrate 1, you get x minus. Now this is what we have to be careful of. When you integrate this, we have to reverse the chain rule. Okay, now everything that you're going to face in P1 in general for this type of questions, you'll be able to reverse the chain rule. These type of questions. Okay, so but generally, when you can reverse the chain rule when the expression is of the form f dash of x times f of x, right? Or you can say, when what's outside the function is of the form of the differential of what's inside it. Okay, so let's say we have f of gx, you have a function inside a function, right? So if you have outside the function something of the form of the differential of what's inside the function, multiplying by that, then you can integrate. So here we can see outside the function there's a constant 1, it's like 1 times, and the differential of what's inside the function is 5, which is a constant. So you have a constant outside, and you have the differential of what's inside it as a constant, so you can reverse the chain rule. And we simply do that by, first of all, adding 1 to the power. So minus 2/3 plus 1 is 1/3. Then dividing by the new power. So we're dividing by the new power, which is 1/3. And then multiplying, and this is where most people forget to do, multiplying by the differential of what's inside the function. So we're going to multiply by 5, the denominator by 5. Okay, and we have our limits between 1 and 2.4. So so I don't run out of space, I'm going to continue here. Pi times, you're going to have x, and they're going to have minus. Now this is 5 over 3. So when you divide by 5 over 3, it's like multiplying by 3 over 5. So it's 3 over 5 times 5x minus 4 to the power of 1/3. And we have our limits between 2.4 and 1. So now we're ready to substitute these values in. But if you want to just make sure that we've done the right thing, so I'm going to cross this afterwards, but if you want to make sure that when you differentiate 3/5 times 5x minus 4 to the power of 1/3, in case you're uncertain or you're doubting that you've done the right thing when you integrated this to become that. Now, if I differentiate this, what should come out is what we started with, right? Which is 5x minus 4 to the power of minus 2/3. So let's see, if you differentiate this, you multiply by the power, so you have 1/3 times 3/5, and then you have 5x minus 4 to the power of, you take 1 from 1/3, you get minus 2/3. And then you multiply by the differential of what's inside the function. So you differentiate 5x minus 4, you get 5. That's using the chain rule. So we can see that here, the 3 cancels with the 3, the 5 cancels with the 5, and we're left with exactly what we started with, right? So we know that we've done the right thing when we integrate it. So you can always check your integration by differentiating your answer. And then you'll know that you've done it right or wrong. Okay, so, and now what we can do is, we can substitute 2.4 and 1 into this, subtract those. So you have, don't forget the pi again. So the volume equals pi times, now we're going to put 2.4 into here. So you get 2.4 minus, and we have 3/5 times. And when you put 2.4 into here, that's 5 times 2 is 10. 5 times 0.4 is 2. That's 12 minus 4 is 8. So it's going to be times 8 to the power of 3, to the power of a third, sorry, which is the cube root of 8. Okay, so we have 3/5 times the cube root of 8. Let me just get rid of this. All right. And then you've got to take away from that what you get when you substitute 1 into here. So you have 1 instead of x, that's 1 minus, and you got 3/5 times, and you have 1 times 5, 5 minus 4, which is 1, 1 to the power of a third, which is 1. So this is 1 minus 3/5. And now we can finally solve this. So we have pi times, we got 2.4 minus 3/5 times 2, because that's the cube root of 8, which is 2, so that's minus, so it's 2.4, which is like 12 over 5. I'm trying to make them over 5. This is like 2.4 is 2 2/5. Okay, 2 2/5 is like 10, 12, 12 over 5. You got minus 6 over 5. And then you got minus, now 1 minus 3/5 is 2/5, so it's minus 2 over 5. Okay, we could put this in the calculator and get the answer anyway. So that's 12 minus 6, which is 6, 6 minus 2, which is 4. So we're left with 4 over 5. Don't forget the pi. Pi, and this is cubic units. Units cubed. Okay, so there's your answer, 4/5 pi, units cubed. So that's how we deal with these questions. Now, I've given you a way using this formula for the general type of problem when you have to find the volume of revolution formed when you take the area between two different functions and you rotate that area around the x-axis. If it was a y-axis, it would be the same thing, except it would be pi. It would be x1 squared minus x2 squared dy. You'd have to make the equation in terms of x and then do it. Now, this method I used is a general method, as I mentioned. We could also use a slightly different method, which most people would use, and the mark scheme actually shows this method. I like to show this general method in case questions like that do come up, and they have started to come up, as I mentioned, where you can't use the other method, which I'm going to show you. So the other method, which is the most common method for this, I'll show you now, is where you consider the area under the curve rotating around the x-axis, and you consider rotating this whole rectangle around the x-axis, which forms like one big cylinder. So if we take away the area of what's under the curve away from the area of what's, the whole cylinder, the area of the rotation of what's under the curve from the cylinder, you will find the area between them, or the volume between them. Okay, so just imagine we take a slice out of this. We're finding the area of this whole rectangle rotated around. So it's going to be one big cylinder. Okay. And then we're taking the volume of what's formed when you kind of rotate this area underneath around the x-axis. We're taking that away, and you're left with, therefore, what's between them. Okay. So we can consider the volume of the whole cylinder. Now that whole cylinder will have it'll be like starting from here, be ending here, and it'll be starting from here. Okay, so that cylinder will have like a radius of this line 1, y equals 1. So that would be like the radius of the cylinder. So the cylinder that we're going to consider is going to have a radius of 1, and the height of the cylinder is going to be this distance here, 2.4 minus 1. So the height of the cylinder is going to be 2.4 minus 1, which is 1.4. That's the height of the cylinder, okay, between these two. So the volume of the cylinder is going to be pi r squared h, which is pi times 1 squared times 1.4. So 1.4 pi. And then we find the volume when you rotate the area under the curve around the x-axis, as we discussed before. And that's going to be pi times y squared dx between those two values. So the volume is going to be of the, that second part. So what we can do here is we can say that the total volume that we're looking for is going to be basically 1.4 pi, which is the volume of the cylinder, minus the integral between 1 and 2.4, between 1 and 2.4 of y squared, which is going to be, as we discussed earlier, 5x minus 4 to the power of minus 2/3 dx. And that should give us exactly the same answer. Don't forget the pi. There should be a pi here as well. Okay, let me just plug in my pen. Running out of ink. Okay, so now we can find that volume. So that should give us exactly the same answer. So 1.4 pi, let me get this ready for fraction. So that's 1 4/5. So 1 2/5. 1 2/5 is going to be, this 1.4. 1 2/5 is going to be 9/5 pi, right? Is that right? Well, not 9/5. That's 7. It's going to be 7/5 pi. So because you're going to have, that's 1 2/5. It's 5 plus 7/5 pi, sorry. Okay. Minus, now when you integrate this, don't forget the pi again. So you have pi times, and now you're going to have your square bracket. As we mentioned before, you add 1 to the power and divide by the new power. So you have 5x minus 4 to the power of 1/3 divided by 1/3 times 5. So we end up getting 3/5 because you're dividing by 5/3. Okay. 3/5 of 5x minus 4 to the power of 1/3. Limits between 1 and 2.4. So that gives us 7/5 pi minus pi times, and then we put 2.4 and 1 in here. So you have 3/5 times 5 times 2.4 minus 4, which, as we said, that's 8 to the power of 1/3. Minus, and we can put 1 in here. So that's 3/5 times, that's 1 to the power of a third, which is 1/3. Okay. And that will give us, hopefully, our answer. So 7/5 pi minus, so this is 6/5 minus 3/5. That's 6, because 3 times 2 is 6. 6/5 minus 3/5, which is 3/5 pi, which gives us exactly the same answer, which is going to be 4/5 pi units cubed. Right? So I've shown you 2 different methods of doing this. Now, some people will say, oh, forget method 1, we don't need it. But if you do get a question, which do come up now, where this is like not a straight line, or this is maybe a curved line between certain values, or not, on a different type of curve, then this method here won't work, because you won't have a nice uniform cylinder to subtract the area from. So you'd have to think about the area between the 2 of these and use this formula over here. Okay, the volume between them as you rotate it around. So this formula is for that type of case where you have 2 different functions. You'll find the area, the volume formed when the area between them is rotated around the x-axis, or as we said, the y-axis. Okay, so just a little summary. In general, if we want to find the volume around, if you're rotating around the x-axis, then in general you have pi times y squared dx. Okay, and if you're rotating around the y-axis, then it will be, the volume is pi times x squared dy. But it's like between 2 different functions. Okay, and you're rotating that around the x-axis, then you're going to have the volume is pi times the integral of y1 squared minus y2 squared dx. And you always, like, the one on top is y1, the one underneath is y2 in that area. Okay, and if that's around the x-axis, if it's around the y-axis that you're doing the same thing, then it's going to be pi times x1 squared minus x2 squared dy. Okay, so that will help you to work out what to do, hopefully. So there we have the end of this question, question number 9 from this paper from May, June 2024. Other questions from this particular paper will be found in the playlist that you'll find linked at the top of the screen, end of the video. Other questions from this particular topic of integration. In general, the integration questions I'll put in this playlist. But the particular questions about volumes of revolution, I'll put here. That's for my P1 collection of Cambridge. And you can subscribe to the channel by clicking on this link. Thank you for watching and see you soon.